So in section 2.8, we're going to calculate the derivative function. Now, what's different about this as opposed to our calculations in section 2.7 is that in section 2.7, we found the slope of the tangent line at a particular point. So instead of an x, we had some value of a. A was equal to some particular number, and then we found the slope of the tangent line at a point. Here, we're replacing that a with an x. And the difference is, because we're using an x, when we're all done, we won't have the slope of a tangent line at one point. We'll have a derived function or derivative that shows us the slope of the tangent line for any value of x that we choose. Now, one of the things that I didn't particularly care for and didn't really understand when I took calculus the first time is that there's way too many notations for the derivative function. You'll see it as f prime of x, but you also see it as y prime, or dy by dx, or df by dx, or d by dx of f of x. And there's some other ones, d of f of x, etc. I'm primarily going to stick to these right here. Maybe that one occasionally, but these are the ones I'm going to stick to. They all represent the derivative of a function. And the derivative is going to tell you the slope of the tangent line at any value of x that you care to put in here. We're going to calculate the derivative, at least initially, the same way we did in section 2.8, break it up into a bunch of steps. And we'll start with an example of the equation of a line. I think this is actually problem number 22 if you actually dove into the book. But we're going to start with f of x equals mx plus b, the basic equation of a line. So, all right, that's kind of cool. Now what? Well, we're going to try and find this quotient and then its limit, more or less the same way we did the last time. So the first step that I'm going to do is find f of x plus h. So in this particular problem, f of x plus h is going to look like this. F of x plus h is going to be m times x plus h plus b. So plugging that in, and that'll simplify to mx plus mh, h plus b. The second step is we need to find the numerator. So I'll call that find delta y, which is going to be f of x plus h minus f of x. We already have f of x. That's just this function up here. So what would it look like here? F of x plus h minus f of x would equal all of this. So let me kind of highlight that a little bit so you can follow things. Minus f of x. So, and f of x is up here. So f of x plus h is mx plus mh plus b minus f of x, and you got to be careful. You're subtracting all of f of x, which is mx plus b. If you distribute this, you'll see you get some simplification. So it's mx plus mh plus b minus mx minus b. And almost everything cancels. Almost everything. Not quite. So let's see. Those cancel and these cancel. No, that one doesn't cancel. This one cancels. So you're left with MH after all that. So basically all we did was we found the numerator of our expression. We found the f of x plus h minus f of x. Kind of like what we did in the last section. You're going to find delta y divided by h. Find and simplify that. And then last but not least, take the limit as h approaches 0 of delta y over h. So let's do those two steps to finish this calculation off. And the results shouldn't really be a surprise when we look back and think about it. So delta y, that's this thing right here, is going to be delta y over h is really mh over h. And that simplifies just to m. And the last part of this is to take the limit as h approaches 0 of delta y over h. You don't have to write that part down. You take the limit as h approaches 0 of just this, of m. Thing is, this doesn't change with h, right? It's just m. It's a constant function. It's always the same. So the final answer is m. All right. Let's see if we can't make sense out of this graphically. Why is the derivative function m? Well, let's think about
The cyclonic blizzard of 1913 is the worst storm.
All right. Thank you. That was good the first time. We don't need it again. Let's see here. Let's do y equals, let's just do a specific example, 0.5x plus 1. So when you're looking at a line like this, the rate of change is just going to be the slope, just going to be the slope of that line. What's the slope of this line in particular that I've got right here?
0.5, right?
0.5.
Yeah, 0.5. Yeah, it's just right here. So a straight line is kind of a boring function because its rate of change is just always the same. It's always changing by 0.5. So not terribly exciting. We just did a general version of that. Instead of y equals 0.5x plus 1, we did y equals mx plus b. So you can play around with that if you'd like. And it doesn't like something that I've done here, but that's okay. Calculation is correct. And we got a slope of m. It's always changing at the same rate. Where this gets challenging is when we have more complicated functions. So let's practice one or two like that, and then we'll look at the implications of the graph. So we're going to go back to our Mars example one last time. And I do hope that this is the last time. So let's look at h of x equals 10x minus 1.86x squared. If we're going to apply our rule here, that is f prime of x equals f of x plus h minus f of x over h. Actually, the limit of that as x approaches 0, then we got some work to do. Limit as h approaches 0. I don't know. Would you feel better if I wrote this as f of x as opposed to h? Yeah, maybe I should do that just so we can kind of follow the model that we did with the first problem. So the first step is to find f of x plus h. And that means plugging in x plus h here. So that's going to look like 10 times x plus h. 10 times x plus h minus 1.6 times x, 1.86 times x plus h squared. This is not going to be a really happy calculation. Sorry, there's nothing I can do about it. Don't shoot the messenger. Well, let's see what we can do with this nonetheless. It's going to be 10 times x plus 10 times h minus 1.86 times x squared plus 2xh plus h squared. So all I did is I squared that out. Now I'm going to distribute the negative 1.86. 10x plus 10h minus 1.86 x squared minus 3.72 xh minus 1.86 h squared. And it's looking kind of long. And yeah, just not much we can do about that. Sorry. Our goal is to find the derived function, the derivative function. And this will tell us the slope of the tangent line anywhere, which would be kind of cool. So let's see here. The next step is to find delta y, which is f of x plus h minus f of x. The good news is that we've already got those things calculated. F of x plus h is right there. And then f of x was given at the start. F of x, that's right up here. So I want to subtract those two. And you have to be careful about subtracting that one. You need to put parentheses around that. Otherwise, you might miss distributing a negative sign. So it's going to be all this here, which is going to be a big mess, but that's okay. 10x plus 10h minus 1.86 x squared minus 3.72 xh minus 1.86 h squared minus 10x minus 1.86 x squared. Wow. There is good news though. We're going to get some good cancellation here. In fact, if you do these things right, for the simple problems that I'm going to give you, not every problem that you're going to could see, but for the simple problems you're going to get from me, this term should cancel out completely. Let's see that it does. I've got a 10x here. That cancels out with the minus 10x here. I've got a minus 1.86 x squared here. The negative times a negative gives me a positive. So that one's going to cancel. For the simple problems that I give you, if that second term doesn't cancel, there's a mistake. I'm not going to give you really crazy problems for which that doesn't cancel. So what am I left with? I'm left with 10h minus 3.72xh minus 1.86h squared. That's all that's left. Let's calculate delta y over h, which is going to be all of this, 10h minus 3.72 xh minus 1.86 h squared divided by h. Now, not only do we want to calculate it, but we want to simplify it. You should see that there's an h that factors out. 10 minus 3.72 times x minus 1.86 h over h. And that h term will cancel out. Finally, I want to calculate the limit as h approaches 0 of delta y divided by h. So it's this term, limit as h approaches 0 of 10 minus 3.72x minus 1.86h. Wow. What's that going to give me?
The 1.86 term's just gonna go away, right?
Yeah, exactly. Because when you plug in the limit, and we can do it at this point, you couldn't do it up here until you cancel the h's, but you can plug in h here, h equals 0, that knocks this term out. You're just left with 10 minus 3.72x. And that is your derivative function. This measures the slope of the tangent line, slope of the tangent line at x, for whatever value of x that you want. You plug it in and get the slope of the tangent line. Let me pause here for a second. Let you catch up or shake your hand out, etc., whatever you need to do. So what's nice is that now that we have that derivative function, we don't have to repeat that calculation every time we want the derivative someplace else. It's just there. Let's see if we can't take a look at this graphically. I'll give you a few more seconds to copy this, and then I'll turn over to the graph. Okay, so let's take a look at the graph. And let me see if I can't make that look a little bit prettier, at least for our purposes. It might help if I squish this a little bit in the y direction. So here's the graph, and you can see what's happening. Remember, this is a rock on Mars. We'd probably want to limit ourselves to maybe just the positive part, but you know, We won't worry about that. Let's just apply it to this function. The derivative tells you the slope of the tangent line. Now, as we move from left to right across this function, what can you tell me about the slope of the tangent line, say, near -1? What -1 for x? So actually, let me just do this. Oops, x. And I'll put a point there. -1, comma, f of -1. All right, there we go. So what can you tell me about the slope of the tangent line at this particular point? And I'm looking for a qualitative thing. I'm not looking for a number. Slope of the tangent line has to be positive, right? Because as you look at the curve, what's happening to the curve as you move from left to right? The curve is increasing. So the slope of the tangent line has to be positive there. And in fact, we could actually calculate the slope of the tangent line. Slope of the tangent line, there has to be given by this formula. So if I wanted the slope of the tangent line at -1, I'd plug in a -1 for x, and I'd end up with 13.72. That's pretty steep. Now that steepness continues and it starts to peter out around where? Where does the slope of the tangent line start to change? Anyone?
Around 3 on the x-axis.
Yeah, around 3 on the x-axis. So let's take a look at this. Let me shut off this part for a second. But the slope of the tangent line is positive until we get up close to around 3 on the x-axis, around here. What's going to happen with the slope of the tangent line here at this particular point, this special point?
It's going to be horizontal.
Yeah, it's going to be horizontal. Now, let's see that by actually graphing the derivative function. And take a look. The derivative function is positive to the left of that point, and then it hits 0 right there. And then after that point, the derivative function is negative. It's negative because this function starts decreasing. The red function starts decreasing at that point. So the derivative is negative. The derivative is showing you the slope of the tangent line. And the fact that it's negative just tells you that the function is decreasing. So nice. Let's do a couple more problems where we're going to look at the relationship between the slope of the tangent line and the function. So are we good with this one? This is a nice kind of warm-up. And in particular, what I want you to notice is how these things match. Right here, the slope of the tangent line is 0. And guess what? Our derivative function is 0 at that exact same point. To the left of this, the slope of the tangent line at points like here, -1 and 6.8, 6.28. At that point, the slope of the tangent line has to be positive. And guess what? The derivative is positive. It's positive because this blue line is above the x-axis. All right. Here's one that you can play along with. I'm going to put this in the chat. So this is a graph of a sine function. And what I want you to do is look carefully at this graph and decide where do you think that this graph is going to have a derivative equal to 0? So where is this graph going to have a derivative equal to 0? It's going to be a lot of places. It's not just one, it's an infinite number of places. But just try and use your mind's eye to think about what it means to have a derivative of 0. That means that the slope of the tangent line has to be 0. Where is that going to be 0?
Can I take a guess?
You can take a guess, but tell you what, why don't you take a guess in your mind and then check your guess by clicking the circle right here. And that'll highlight the places where the derivative is 0. And just tell me, were you right? Let's find out.
Oh, hold on, because I didn't even open it. I didn't realize the answer was there.
Yeah, so this one allows you to actually cheat, you know? You can run ahead and get
I
the
didn't realize
answer.
you made it that easy. Sorry.
I apologize. I will try not to make things easy ever again.
Not what I meant.
All right. So every place where the function has a little peak or valley is going to be a place where it has a derivative of 0. It's going to have a horizontal tangent line. So all these blue lines right here. Now, let's figure out something else. Where is it going to have a tangent line with a slope of 1? Well, that has to be where the graph is going up someplace. And a good guess would be maybe right here at -2 pi. Where else do you think the graph would have a slope of a tangent line would be +1? What would be another point?
0.
Yeah, at 0 and at pi. So at these places, the slope of the tangent line is going to be 1. But there's also some places where the slope of the tangent line is going to be -1. So where would some of those places be? You can list them out for me.
-3 pi,
Good.
negative
Thank you.
pi, and then
Yep,
-3 pi.
-3
Yeah.
pi, -pi. And in fact, if you wanted to click this next circle, I'm sorry, Alejandra, this again is going to be easy.
You'll
There you
never
go.
let that go now.
It might stay with us for a while. So what I've done is I've plotted the places where the derivative is 1 and -1. And that's starting to kind of fill out the graph of the derivative. Now keep in mind that the graph here that we have is a sine wave. What is this? What do these purple dots seem to be filling out? What graph do this seem like they're like?
Cosine graph.
Yeah, it looks like a cosine graph. And if we click one more circle, we fill in the cosine. So the derivative of the sine function is actually the cosine function. That's something we're not really going to go over for a couple more sections, but just giving you a little bit of a preview there. Now I want you to experience this connection between the function and derivative in one more way. So last Desmos link for the day, and then we'll finish up with a couple problems that you might see in the book. But this one right here. And this one's really cool. I want to hear a lot of ooh, ah, because this one's kind of cool. And while you get there, I'm just going to click this little tool icon in the upper right-hand corner. And if you click the capital A, it just makes your graph a little darker, a little easier to see.
Wow, this graph is phenomenal. Good work.
Hey, that's great. But wait, there's more.
Oh, man.
Yeah, I know. This is really cool. So this is, again, the graph of the sine function. And what I've got here is in red, a little highlight of the slope of the tangent line. So right at 0, the slope of the tangent line looks like it's positive, looks like it's about 1. And what I want you to do is slowly trace out the graph of the derivative at the same time you're moving the slider. And it's going to stay on the function but you're going to see how the graph of the derivative or the slope of the tangent line corresponds to this graph. So, all right, now we're ready for you, Cole. So there you go. So as this
Wow,
moves, yeah,
look
that's
at that
good.
go.
Yeah, awesome. So let's take a look at the function at this one point right here. Now at this one point here, what do you expect for the value of the derivative? What's the slope of the tangent line going to be there? On the blue graph, can you use your mind's eye to imagine what's going to be the slope of the tangent line? That horizontal line? 0. And watch what happens to the green graph as I get to that point of 0. The green graph is going to touch the x-axis. So right there at that point, the derivative is 0. And then past that point, the function starts picking up again. So the derivative is positive. It's going to stay positive until it gets to the top of this next hill, in which case it's going to come back down to 0, and so on. And you can kind of move it back and forth. And maybe you want to spend a little time outside of class just playing with this and starting to get the relationship between the function and its derivative. It's an important relationship. And a lot of the homework problems surround that kind of question. So let's finish up with a couple of those homework problems. Let's start with this one. So for this one, this is the graph of a function, and they want you to come up with the graph of the derivative based on the graph of the function. Now, we're not going to try and be terribly precise about this, but notice that the graph here is kind of steady, but does it have a positive slope or negative slope?
Negative.
Negative. So the function is changing in a constant negative direction, so its derivative is going to be negative. And the graph of the derivative, which I'm doing in yellow here, is going to look about like that. And then we're going to switch over. What happens to the graph after this point? The graph starts increasing, right? So the derivative is going to be
Positive.
positive. And it's probably going to be a little bit higher than this one was low. So let me put it up here. So it's going to be positive there. And then down to negative again. So it's going to be negative until we get to this point, and then positive right here. So a bunch of little steps for the graph of the derivative. Nothing too glamorous there. Now in this next one, which comes directly from your book, they've given you the graph of the derivative. That's, 1, 2, 3, or 4. And they want you to match the graph of the derivative with the graph of the function. So I'll do a couple of the easy ones here. I'm starting to talk loud so that my dog doesn't come through on the recording so much. Well, let's start out with this one, because this one should be very similar to the one we just did. Moving from left to right, in this range right here, what could you say about the derivative? What's it going to be like? If you're looking at this function, this little piece here, the rate of change of that is going to be positive or negative?
Positive.
Going to be positive. So it's going to look like this. And then the function starts decreasing. It's decreasing from here until we get to this point. So you're going to have a negative derivative. And then last but not least, you have a positive derivative for this last part right here as the function is once again increasing. So it's going to look like this. Now, one of the things you might notice is that the endpoints of these things are empty. They're hollow dots. And that's because the derivative doesn't exist at certain points. So what kind of places are going to fail to have a derivative? Well, there's 3 places where a derivative would fail to exist. And let me write those down for you. So this is good to know. It's kind of like imperative to know. Places where f prime of x does not exist. The first one is if the function is discontinuous. If x or f of x has a discontinuity, then at that point, the function is not going to have a derivative. Another place that the function is not going to have a derivative is if at x equal a, f of x has a vertical tangent, then f prime of a won't exist. And finally, if f of x has a corner point, and I'm being really loose here and just calling it a corner point, if f of x has a corner point, at x equal a, then f prime at a won't exist. So quite generally, 3 sets of points are going to be places where you're going to have a derivative that won't exist. It has a discontinuity or a vertical tangent or a corner point.
Sorry, could you repeat what a corner point is?
I haven't really defined it much for you, but I was going to show you as soon as I gave you a chance to copy this down. Yeah, a corner point is just a place on the graph where it has a sharp point. Not like a parabola, not like y equals x squared, but more like the graph of the absolute value, y equals the absolute value of x. So if I can switch away from this right here, you've got a corner point. That's a corner point. That's a corner point. So the derivative is not going to exist there. And the reason that that's true is because the derivative is really based on a limit. It's the limit from the left and the limit from the right. Well, the slope of the line, the slope of the tangent line, just to the right of this and just to the left of this don't equal each other. In fact, you can see it in the graph of the derivative. You jump from here down to here. So you're not going to get a derivative at those corner points. And I don't think I have a graph that shows a vertical tangent here in my examples, but if you wanted to see a graph of something that has a vertical tangent, let me just show you an easy one. Y equals the cube root of x. Now I'll write it a little differently just to save myself some grief, but at x equals 0, you've got a vertical tangent. Let me see if I can't blow that up a little bit. Yeah. So the graph of the tangent line is vertical. And you may remember from your algebra classes that the slope of a vertical line is undefined. So that's a place where you can find the derivative not existing. And then y equals absolute value of x. I don't want yu, just y. There you go. Has a sharp corner point right at 0. And so again, that'd be a place where the derivative wouldn't exist. And the last place is just continuities, discontinuities. Okay. I think I was a little bit late in getting you out the other day, so let me call it quits here. Is there any last minute thoughts or questions on some of this stuff? Anything I can clear up on what we've covered? I might touch on a little bit of this stuff on Monday of next week, but I think we've gone through most of it. So like I said, I might extend the deadline on the homework just to give you a chance to ask some questions on Monday of myself or Mimi. But is there anything else on all these things? Yeah, I think I do want to do a couple more problems. If you do charge ahead and see some of these things where they give you the graph of f prime and f double prime, you have to figure out which one's which. What you have to do is you have to pick one of these, say, all right, if this was f, what would be the derivative graph? What would it look like? And then once you have that graph, what would the derivative look like again? So it's just a little bit of a mind game. Maybe we can cover that on Monday.
Oh, I had a quick question.
Yeah.
Was attendance ever taken? I just wasn't really
No,
sure.
it wasn't. It wasn't. I'll
Okay.
do that right now.